using Linux a little bit more because apparently I have to sort of outline this in more detail verbally. But I do want to say that your cards should all now work in the door. And assuming that you were signed up for the class day before yesterday. And so you should have access all weekend. With that comes the following conditions. At no time will you block the door open. If you're in the lab and the door is blocked open and I walk by, you will lose access. Okay, it doesn't matter if you blocked it open or not. So if you're in the lab and the door gets blocked open, close it. This is for security. Experience shows that people don't like to lock other people out of the lab, and so there's a tendency for the door to stay open all weekend, which I do not want. Do not do that. Also, nobody should be in the lab that doesn't have card access. So if they don't have a card, don't let them in. This includes your friends. Can't be in the lab outside of hours, of course. From 8 to 4, it's okay with the staff here, but outside of office hours, nobody in the lab doesn't have card access. You're going to need to use the combo that was on the board to get hardware out of the cabinet. The FPGA boxes have a power supply and a couple of programming cables in them. And the reason I keep the power supplies and the programming cables with the FPGA in the boxes is that the power supplies are the same ones that are used by 2300. And so if I leave them on the table, they're gone. In fact, there's 5 times as many 2300 students as there are you. So anything you leave on the table will probably be gone. Also, in all fairness, you should pick up your stuff. No Ethernet cables laying around, no monitors left on the table. Make it look nice for the other class. There's a Ethernet switch on each set of tables in the middle of the group of tables, and you can plug your FPGA into that and get a wired connection into 10 space. No other device you put on those switches, for no one thing, it won't work because the switches are locked down with respect to MAC address. So you cannot plug your laptop in, and to do so would be violating EC policy because you're now putting your laptop on a secure network. Don't do that. Saw a couple of people detaching USB keyboards and mice so that they could plug them into the FPGA like you would a Raspberry Pi, except it doesn't work. These are not Raspberry Pis, and it makes lab maintenance extremely difficult if you disconnect keyboards and mice, so I will yell at you if you do that and jump up and down. Don't do that. These devices are configured so that the console input is a pure serial line directly off of the arm. And all communication will go through PuTTY or MobaX term or whatever terminal you want to run on the PC, but basically through a serial connection or through SSH. There is no user interface, there is no GUI. If you want to download another version of Linux, besides the one we're using, you can run a GUI. I won't support it though. So leave the hardware attached. Don't disconnect the monitors to attach the FPGA. We have probably 25 spare monitors in the room. Take one down, plug it in. No hardware leaves the lab, except your SD card. If you want a FPGA at home, buy one. They're fairly cheap. You get one from Taiwan in less than a month for about $175. That's in time for final projects, but just barely. When you get done, put the stuff away and keep the lab nice and clean. So, with all that admonishment, you can get in the lab anytime you want. You can be in there all day and all night, all weekend. Probably later in the semester you will be. So, any questions on lab protocol? Okay, enough preaching. Let's talk about, well, first of all, are there any questions about the last lecture? You know, like they said at Woodstock, if you can remember, you weren't there. It's like, this is like the last lecture was, if there's no questions, you weren't here. The Qsys is okay. We're going to talk a lot more about Qsys. So going back to the ARM Linux page, which by the way is required reading for Lab 1. The very first thing you're going to do is download this image for the card. It takes about an hour in the lab because the Wi-Fi is so pathetically slow. We're working on that. It should be ready by next year. Yay. But for right now, you're much better off walking into the hallway or out into Duffield to download the image. It'll be 2 or 3 times faster, maybe 10 times faster. You're going to, there's an M select switch on the bottom. It's a mode switch for the FPGA. Don't mess with it unless you have to. It should be in the correct position from last year. So if you find you can't program the FPGA through the USB blaster, then come talk to me and we'll figure out what's going on. You're going to need to download a bunch of stuff. You're going to need to get at the very least, an SSH client. But before you do anything else, you need to put a password on root and disable the Linaro account, which I left enabled, and that's how somebody got in and took over my system. Oh, and just like every other Linux system, this Linux system does not just be powered down. You need to do an orderly shutdown to avoid corrupting the SD card. So whenever you turn the system off, whenever you cycle the power, do a shutdown -H now and shut the thing down in an orderly fashion so that you don't corrupt the SD card, which by the way, I suggested the very first thing you do after you get the operating system just the way you like it is back it up. Back up early and often. You're going to be in 10 space. You're going to have to issue a bunch of commands to put the system in 10 space. It outlines how to do that here. You're going to SSH in or use PuTTY to get in. But you can't use SSH until you get the networking set up. So for a start, you're going to be coming in through a serial connection. The serial connection assumes that you have physical access to the machine, and therefore has no password on it. It comes up logged in. So you can get started even if you don't remember the password. But once you have a password on it, you'll never get it back again unless you write it down. GCC runs on this. Most of my examples have a 1 line at the top which gives the flags for compiling. And you're going to want to do this. you're going to want to follow that. You can that's probably enough of that, but follow these directions. Just go through it, and you can not do some steps if you want, but go through that and follow what you need to do to get it set up. Are there any questions about Linux on this box? I know a few people haven't completely run it. Yesterday, it took them, by the end of the lab period, they had it run. Let's talk a little bit more about Qsys. We started this last time. In the bad old days, when you were going to lay one of these things out, you did some system like this where you had to have a bus arbiter for multiple masters, and you had to do address decoding and adapt widths and make sure you're driving all the lines. And what Qsys does is to hide that from you, so that all of this, the arbiters and burst adapters and packetizing and command flow and data flow, is generated by Qsys written Verilog. And like anything else, when you abstract that away, you lose something. You no longer have control about how the system communicates, but you gain a lot in that you can do more, you can go further. And that's what we're going to use. We're going to ask you to start out by using the processor actually as a 32 or 64-bit master, and write a bunch of, put a bunch of slaves on in the form of I/O ports that are pre-written for you. You just drag and drop them onto the Qsys design area. But sooner or later you'll be writing bus masters, which require some actual coding. As I said, the system is hierarchical. So if we look at the VGA subsystem module, it's actually a subsystem that we talked about last time for the 640 by 480 SD-RAM controller. You can open that up and you will find a whole pile of stuff in there, including another phase lock loop, because it has to run at 21.175 megahertz, a DMA controller, a FIFO, a resampler which allows you to change the width of each pixel, and a whole bunch of other stuff. So Qsys is hierarchical, and you might want to right-click on a subsystem to find out what's inside of it. In general, a Qsys master can generate addresses. Qsys slave responds to addresses. Any questions on this? You should probably read through this. Oh yes, there are, the modules that are available include a large number of modules, but one you're going to need to know about is the parallel port. And I suggest, rather than looking at the Embedded IP Users Guide, which is massive, look at the University Program PIO document, which abstracts out kind of what you need to get this running. And the basic device, the parallel I/O port, which is written for you, has a clock input, it has a reset input, it has a Avalon slave port, which you will then drive from the ARM, from the HPS, and then a potential interface which is mapped not to the bus, but back into the FPGA. So this becomes an interface then between the Qsys bus on one side and the FPGA fabric on the other side. And you can specify all kinds of stuff, including the width and whether it's an input port, an output port, or a bidirectional port. And you really do need to read this because it gives you the memory map for the I/O port. So you really do need to read this probably before, probably during the second week sometime in the lab. The rest of these modules are really interesting, but you don't need them right now, except for you may need memory. Yeah, maybe not, but it depends on how you do the interface. There's lots of information on memory, and we'll talk about that later. But there are modules for doing a cascaded integrator Foucault filter. Does anybody recognize that name even? That's a rate-changing filter for doing multi-rate sampling. Finite impulse response filters are already written, FFTs are already written, numerically controlled oscillator, parallel port, UART, audio core, video core. Going to need that one for lab 1. You'll mostly just be using the video core, but you may want to know how it works. And this description is fairly straightforward through the first half, and then completely inscrutable in the second half. But you only need the first half. There are some videos on how to use the interface on YouTube. And we'll talk about Avalon Bus Masters later. Unless there's some questions right now. Mainly what I want to talk about today is the next step in the checkoff procedure. So week 1 is simulation, week 2 is to put your code onto the FPGA and then use one of these two, I guess I better refresh the page. Either signal tap or OLA to debug your core, your solver on the FPGA. So this is not simulation. This is allows you to read out the internal state of a running module where it's running on the FPGA. Signal tap is, and it's your choice which one you use. Signal tap has a point and click interface. You identify the module to the software. You click on the signals that you want to monitor. Signal tap builds the circuitry to do that, uses the memory on chip to record what you want to see, and then blasts it out through the JTAG connector, through the USB blaster port, back to the PC, which displays waveforms for you. So that's a no programming interface. There's a tutorial from Intel Altera. There's an online course. There is a gigantic description in Chapter 10 and Chapter 14 of the Qsys Volume 3 handbook. I think that's about 2,000 pages total. But the overall interface looks legit. But you're going to add nodes to the instance where nodes now are any signal that you want to measure. And to test this, to motivate it, I made an extremely simple module, which just is a counter. So it has a reset signal. It resets the count to 0, and then it does a 40-bit count. So it's just as simple a possible state machine as I could possibly build. So you're going to you look at this thing, and there's all kinds of fields, but, so I put arrows on because I can't necessarily see these dimmed out things. It says, double click and add nodes. So you double click here, and it blows out an interface that says, here's all the nodes that are available, what do you want? Once you get this all set up, then you're going to select a clock. In this case, it was clock 50. That's a 50 megahertz clock. You probably would use something faster on the current setup. And then you're going to set up a trigger condition, because there is no way that you, operating a push button, are going to find anything useful on a system running at 50 megahertz. So there has to be some internal trigger condition that says I want to collect data, like the reset line falls and bit 4 goes high. And when those are both true, then it collects data. So you have a menu here that allows you to check rising edge, falling edge, on high, on low, don't care. Again, completely point and shoot. But the reason I want you to do this in Lab 1 is that you will find this to be useful throughout the course, and if I don't force you to do it in Lab 1, you'll never learn to use it. After you've got this all set up and the trigger occurs, then you will see a window on the PC that gives you the waveforms with a 1 clock resolution, with a clock cake resolution from clock, so 20 nanos. Straightforward to use. There's a couple of quirky things. Qsys has a tendency to optimize away signals for you. And so the signal may not exist if you try and signal tap monitor it. So to get around that, you may want to occasionally use the synthesis directive on a wire or a register. Now, this is a weird construct because it looks like a comment, but it's a directive to the compiler. So if the first word that occurs in here is the word synthesis, then the next word is a directive. Now what happens if you write a comment whose first word happens to be synthesis? I don't know. Don't do that. And yes.
Does it still do it if you just do 2 slashes and without the?
No, it does not. No, has to be /*. And oh, by the way, it has to be before the semicolon. If it's after the semicolon, it's just a comment. Or horrible syntax. But so if you are looking for a signal and say, it's not here, then change it to synthesis keep. There's also a couple of other utilities that are fairly new, and I haven't messed with them at all. One's called Signal Probe, that allows you to, with very little recompile, to route signals to output pins. So you can look at 1-bit signals on I/O pins. That's useful if you're looking at, say, a couple of low-dimensional signals like memory enable or write enable lines, where you need to see if the write enable time is timed correctly. But Signal Tap will do bus designs and record whatever you want to record, however many signals you want, as long as you have enough on-chip RAM to record all of the data. That being said, The counter as written took 17 logic modules. When I added single tap, it was 390. So the single tap completely dominated the design by a factor of 20 or so. Now, with bigger designs, it would be more equal. The design would be more like the size of single tap. But it's a fair amount of logic, which implies that it takes a while to compile. Any questions on this? You really need to play with this. You really need to just, yes, Josh?
Does the OLA add logic elements as well?
So the OLA, well, thank you for the lead-in. The OLA logic analyzer is quite minimal. It does add logic, typically not very much, because it doesn't do very much. All it does is to put a 32-bit word, the data you want to debug, into memory as fast as it can, and waits for a trigger event. And after the trigger event, it puts in a little more data, depending on how much post-trigger data you want, and then throws control back to the HPS. So this is merely a data logger. All it does is to wait for a trigger and memorize data at bus rate, throws control back to the HPS, and then the HPS can do whatever it wants with the data. For instance, it can plot it. So this happens to be a three-phase sine wave generator, a three-phase direct digital synthesis sine wave generator. This is the phase counter at the top. These are the three phases of sine wave, and these are the 1, 2, 3, 4, 5, 6, 8 bits of the phase counter plotted as logic. It's zoomable. It's scalable in height, but none of that stuff is on the FPGA. That's all on the HPS. So the goal here was to use as small a footprint on the FPGA as possible and put as much onto the HPS as possible. The interface, though, is a programming interface. So let's say we have this device under test. This is the direct digital synthesis sine wave generator. This is the phase accumulator here. We're taking the top 8 bits or so of the phase accumulator and then running that phase into 3 copies of the sine table at 0 phase, 85 plus 85 plus 170, which is 120 degrees, and 240 degrees converted into a rotation of length 256. So that's the device we're testing. It's got outputs here which are sine out 2, sine out 3. It's got a phase. And the way we're going to connect it to OLA is to write 2 lines of code. We're going to say that the data input to OLA are the top 8 bits of each 3 sine waves and the phase. So 32 bits. Can be any combination of bits you want, but in this case it happens to be 3 waveforms plus phase. Kind of like what you might need for debugging Lab 1. And then the trigger source, I just threw a bunch of stuff in to see what would happen. Key 3, it's a push button, bink. Some zeros because I needed 32 bits. All 16 bits of sine out 1, and all 8 bits of the phase. again, adds up to 32 bits. And so if I chose a trigger mask which included the high order bit, then when I pressed the key button, key 3 button, the system would trigger. And that is what is shown here. It's fairly close to 0 phase, but it's not 0 phase. It's just wherever I happen to push the button. Bink. Oops. We'll go back here. If I modify the trigger word slightly to trigger mask to FF, if I modify the trigger mask to FF, then that is isolating the low 8 bits of the trigger word, which is the phase, right? Now, if I give a trigger value of 0 and triggering off the phase, we will get a trigger event which happens at phase equals 0, which it in fact does here. Now I modified the trigger again to modify the device under test actually to have a reset line. So the phase accumulator now has a reset condition which forces it to 0, and then a free run condition which increments it. So when we hold the reset button down, we lock the phase at 0. When we do that and set up the trigger source to be slightly different now, so that there's key 3, DUT reset, 6 bits, 16 bits of 0 in the phase, then we could trigger off a phase or either of these 2 push buttons. I believe this was on key 1. Now, when we push the button, we get this. So the phase stays locked at 0. And why does it stay locked at 0? Because there is no way that you can lift your finger off that button in 5 microseconds. So you push the button, and while the button is still down, it acquires 500 samples and stops. 500 samples at 100 megahertz. So I just locked the whole system at the phase 0 point, effectively by pressing that button. And that's where the trigger occurs for the logic analyzer. So you can make a fairly general trigger condition. You can debug any 32 bits you want to. If you modify the source code for the Qsys, you can do more bits, but 32 is probably enough. Certainly it's enough for lab 1. And furthermore, we haven't talked about the C code yet, which runs on the HPS to actually do this formatting. But one nice thing is that if you get any output onto the screen at all, this is a putty dump of the 3 signs formatted as a pleasing table. Then as soon as you get it output onto the screen, you can redirect standard error. I've outputted this thing under the unit standard error. You can redirect this with no change in the code to a file. This is now just a text file, which you can then use however you wanted, but in particular, You can insert commas into the formatting and make it a CSV if you want it. Formatting is under your control. So you can log data to a file, which could be useful for documenting something for, say, a lab report. Also added a couple of Gpio pin outputs for the oscilloscope. This is like the signal probe, but scaled down a little bit. So any of the 32 bits that you choose from your data word can be outputted by flipping the switches to the correct position to choose the two 32-bit selectors. And now we're looking at, I don't know, a couple of bits out of the phase. And the reason this has so much hideous ringing on it relative to this one, well, first of all, there's a 100 megahertz signal coming into a 100 megahertz bandwidth oscilloscope. But I put one ground here on that bolt, and another one over here, and the one on this bolt has less noise from the output here than the ground that's on the other side of the board. Just going to show the speed of light is real. So you have the ability then, using OLA, to, by dropping a module into the Verilog, oh, you haven't seen that yet. I've got time to look at that. So let's look at the Verilog. There's the usual stuff, all the I/O from the board. Then there's a device under test section. That's all you have to modify, is the DUT section, which here has the reset and the state machine, and the connection of the logic analyzer to DUT. So you need to specify a data input and a trigger source, and that's all. The rest of the Verilog, of which there is quite a lot, because the whole logic analyzer is in one file, and the sign tables and everything else for the example, stays the same. So you could chop out my DUT, put in yours, with not too much editing. Now, that's part of the story. I've said that everything is unloaded onto the HPS. What sort of mess is that? Well, first of all, there's the line that tells how to compile it.
You said we need to replace.
You need to give the trigger source whatever you want to trigger off of. Could be reset if you want to get the first. If you want to get the first 1,000 or so example cycles. It could be a counter that's counting up, and you wait till the count is 1,000,000 before you record the data, so that you're in a steady state solution. Whatever you want. There's a header here, logic analyzer interface, which you could read if you're amused by such things, but is not necessary for actually using this. This is stuff I coded up for you. There's a draw routine, which is, go back and talk about this a little bit. There's a start OLA, which takes a trigger mask and a trigger match value. This is the thing you want. These are the bits that matter. These are the value of the bits that matter. It starts it and freezes the HPS until the trigger occurs. When the trigger occurs, it returns the data. When you get done, when your HPS program gets done doing whatever it's going to do to this data, you do an end OLA, which says that you're ready to go off and do something else. There's a print binary call, which has a bunch of obscure fields. The beginning bit, I'm sorry, the index of the first sample you want, the index of the last sample you want, the position of the lowest bit in the data word, the number of bits from the data word, and whatever title you want to put on that column. There's a wave, draw a wave, which takes the low bit, a bit mask. So this is the rightmost bit of from the data word. This is the width of the number of bits, whether it's signed or unsigned. There's an interesting technical reason why that has to be specified. I'll see if you can figure that out. The position you want to put it on the screen, the scale you want, the horizontal scale, and the color. So these are fairly high level calls, and that's all there is. So now we go back and look at the code. And there's a whole bunch of graphic stuff that's defined, and a whole bunch of graphic support that's defined, and the virtual memory variables, which for this you do not have to mess with. That's been abstracted away. How do you convert hex to binary? I made a table of the decimal strings that looked an awful lot like the binary strings. It's crude, but it works. You get all the memmap bus addresses and all that stuff that you have to do. Then, in the while loop in main, I just ask the user to provide a trigger mask and a trigger mask value, and a zoom value, horizontal zoom. And erase the screen, draw a couple of things, and then do a start hold. This does not return until the trigger is successful and the data returns. Is in an array. It's actually an SRAM and it has to be copied by the HPS into its own memory. Then I do a bunch of draws. This starts at bit 0 and goes for 8 bits, unsigned, at position 100 on the screen with scale factor 2. To do a 1-bit waveform, you just set the mask to 1. This is an 8-bit waveform. This is a 1-bit waveform. This draws the 3 sine waves. And then there's some printing stuff that goes on. When you get all done with that, with all the printing stuff, you do an end OLA. That says that it is fine for the data acquisition system to start up again and start collecting data on the FPGA side. So when you do an end OLA, it triggers a circular buffer to start accumulating data all the time. So it just sits there blasting away phase and sign data into memory until the trigger occurs, and then it freezes it.
So what happens if your trigger never goes?
Program hangs, and you hit Control-C. Crap, what happened here? You go back and look at the Verilog. There's more documentation. All the interface stuff is here with all of the various options for what unsigned means and signed means. But the heart of it is that you should be able to put a device under test into the Verilog, and you should be able to write the draw commands or the print table commands that you need to look at the the logic output without doing very much else. I really like the printing in binary, it turns out, is more tedious than it looks. But, so this is the binary string that represents each of these, and with a trigger sample indicated here, in case you want to really get down and dirty with the bits. And that's all written for you. So you have your choice for the second week checkoff. You can go for a point and shoot interface from SignalTap, or you can go to a programming-based interface in the form of OLA. Either one will work, because all I want you to do is to validate that you're getting the same waveforms that you got under simulation. Neither of these systems, neither of these debuggers will be considered a final product. In other words, you cannot use either one of them for the final product in week 3 in which you draw an interactive waveform. This is only for testing your module with the minimum amount of programming work to show that your compute module is correct, and to teach you how to use the debug, how to use the SignalTap or OLA. Any questions on this? You might want to read this page. Unlike most of the pages, the way I normally do these things is I would start with a specification. The specification is here. I get something running, barely running. I write about it, get the chip planner, find out how much space it's taking on the FPGA, do some 5% of the ALMs and 1% of onboard memory. That's okay. Do some estimates of feasibility, and then start iterating it until I get to something that's more or less a final product. Then what I do, since nobody reads anything anymore, is to take the result and put it at the top and say, if you care about the details, keep reading. I haven't done that yet in this case. Therefore, the conclusion of this that you're going to want to use is at the bottom of the page, where it says, as a template for testing lab 1. That's what you want to look at. So I'll be happy to answer questions about this. I think, of course, that it's easy to use because I wrote it. But I'll be interested in hearing what you have to say, because that'll probably change the way I have the directions written for it. Any questions about this? Any questions about lab protocol? We'll hand out SD cards and show you where the cables are and the boards are and all that kind of stuff this afternoon in lab. About 10 people were there yesterday, so there should be about maybe 20 people there today, depending on how many people are still in the class. You have access? Check your card to make sure it works today. Okay, thank you.
Got that SD card. Did y'all,